Welcome back. Let's try to solve a few more questions, and with these questions we'll end up our portion of statics. We are given a question that determine the moment of inertia with respect to the x-axis for the circular area shown. We are given a circular area and we have to determine its moment of inertia about the x-axis. Okay. Now, in order to determine the moment of inertia about x-axis, first of all, we know that moment of inertia along x-axis has the formula. Moment of inertia along x-axis is equal to integral of y square dA. So first of all, we have to find out we have to designate something as our area element. As far as the area element is concerned, the area element that has been selected here is again in the form of a rectangle. This is a small area element that has been taken. We call this as dA. As far as dA is concerned, the x coordinate from here to here, as measured from here to here, is equal to x. Okay, so this is equal to x. This distance is x. So as this rectangle is symmetric with respect to this origin, therefore this also taken as x, as is given here, x and s. As far as its thickness is concerned, it has a very small thickness that is equal to dy. As far as dA is concerned, the area of this rectangle, small area element, will be equal to its total length, that is 2x, multiplied by its height, that's equal to dy. So 2x multiplied by dy is equal to the area of the small area element. Now, as far as the centroid of this area element is concerned, we know the centroid is at the geometrical center. Okay, it's on this line. It is at a distance. The distance of the centroid of the area element measured from the x-axis, we take that as equal to y. Okay, therefore, as far as the moment of inertia along x-axis is concerned, that will become equal to integral of y square dA, and our dA is equal to x dy. Okay, now we have two variables, x and y, and our variable of integration is y. So we have to find the relationship between x and y. We know as far as the circle is concerned, the equation of the circle is x square plus y square is equal to the square of the radius. Its radius is a, that is a square. Okay, so as far as x square is concerned, we can write x square equal to a square minus y square. Okay, and as far as x is concerned, x becomes equal to under root of a square minus y square. Okay, this is plus or minus, but we have to take only plus value. Okay, so this is the value of our x. So we'll substitute this value of x back into this equation. Okay, so we will get, therefore we will get the moment of inertia ix will be, ix is equal to integral of y square, that is y square, then we have 2 times x. As far as x is concerned, x is equal to under root of a square minus y square, and then we have our dy. Okay, the variable of integration is dy. Look into the variable of integration. Why is the variable of integration? As we move, this area element has to translate from this end to this end. Okay, on this side, the value of our the value of our y is at this point is minus a, and when this area reaches here, its y coordinate becomes equal to plus a. So the value of our variable of integration varies from minus a to plus a. Okay, so as far as this integral is concerned, this is a very famous integral we all already know. So we can perform this integration. 2 will come out. This will be integral of minus a to a under root of a square minus y square, and then you multiplied by y square dy. Okay, so we can now perform this integration. Okay, this integration is well known to us. Okay, even if we don't know the direct value of this integration, we can use the formula, uv formula, integral uv, that is u into integral v minus integral differentiation of u integration of v. Okay, we will use the uv formula. The final result for moment of inertia along x-axis after performing this integration, which I am leaving as an exercise to the students, will be pi by 4 a raised power 4. That is the moment of inertia. The moment of inertia about x-axis is equal for a square, so sorry, for a circle, the moment of inertia about x-axis is equal to pi by 4 a raised to power 4. In the same way, if we find out the moment of inertia about y-axis, okay, then our area element, if we have to find the moment of inertia about y-axis, then our area element will be like this. Okay, this will be then our area element, which will be at some distance from the origin. Let's call that distance will be calling as x. Okay, the total will be 2y. Okay, so the procedure will be same, except that dA, the small area, will be now equal to 2y and this small thickness, that is dx. Okay, and the formula is again x square plus y square is equal to a square. The same procedure is to be utilized to find the moment of inertia about the y square. By the way, if we perform that, that will also come out equal to pi by 4 a raised to power 4. Both these moments of inertia along x and y axis are same. This is one important thing that the students should be knowing. Another is, as was asked by few students about composite objects, like we have a composite object given in this example. We have a rectangle. Its dimensions are given to us, and within this rectangle a circle is cut. Okay, we are asked to find the moment of inertia about the x-axis. We have to find the moment of inertia about x-axis. So what we will do, this is a composite object for us. Okay, this is actually, this is equivalent to, this diagram is equivalent to a rectangle, full rectangle, minus a circle of radius 25 mm. First of all, what we will do, we'll find the moment of inertia of this rectangle about x-axis. We'll find the moment of inertia of this circle about x-axis. Then we will subtract from the moment of inertia of this rectangle about x-axis, we will subtract the moment of inertia of this circle about x-axis. That will give us the moment of inertia of this composite object. Okay. As far as the circle is concerned, look into the circle. We know the moment of inertia of the circle, about an axis, the moment of inertia of the circle about an axis passing through its center like this, okay, is equal to the moment of inertia of the circle is about this axis is pi by 4. Its radius raised power 4, that's pi by 4, 25 mm raised to power 4. This is its moment of inertia. This is the moment of inertia of this circle about an axis passing through its center. That's in fact its centroid. Therefore, we can use the parallel axis theorem to find the moment of inertia, its moment of inertia about this axis, about this, which is our x-axis. That is the moment of inertia. We can use directly the formula. The moment of inertia about this axis, that is Ix, will be equal to its moment of inertia about the centroidal x-axis, that is pi by 4, 25 mm raised to power 4, 25 mm raised to power 4, plus this parallel axis theorem, plus area times, plus its area. Its area will be pi r square, that is pi 25 mm square, pi 25 mm square, that is, and square of the distance between these two axes. The distances between these two axes is 75 mm. So it will be 75 mm square. Okay, so this formula, this will give us the moment of inertia of this circle about x-axis. Okay, now we will calculate the moment of inertia of this rectangle about this axis. Okay, we have already calculated that, and moment of inertia of a rectangle about its one of its base is 1 by 3 bh². Okay, we know as far as b is concerned, we already know the value of b, that is 100 mm. As far as h is concerned, that is 75 plus 75, that is 150 mm. So we calculate, by this formula we will calculate the moment of inertia of this rectangle, okay, about this axis. From this value we will subtract this value. From this moment of inertia we will subtract the moment of inertia of the circle. Therefore we will get the moment of inertia of this very composite figure. Okay, this much the students should be knowing. These are the fundamental problems. The students should try to consolidate on these problems, revise them, and go ahead with as many problems as possible. This is where we finish our portion of statics, and the next lectures coming up will be about the dynamics. Thank you very much.